Hello, this is Miraj Patel, and today we're gonna begin talking about energy. And today we're just gonna introduce some of the formulas and terminology about work and energy. So, first, what is the definition of work and energy? And in physics, work is defined as a situation in which a force is exerted and there's a displacement of an object due to the force. So basically, in physics, uh, if we have a force and it moves something, we have work. And whenever there's work done, there has to be energy transferred. So this is how we can relate work and energy to solve problems. And basically, work, the work in a force or object does is the product of the force in that direction of the movement. So if we are pushing on a block, like in this picture, and we're just pushing straight forward, and the block moves straight forward, we just multiply what we pushed with, what force, and how far the block moved. So if it's directly aligned and you're pushing the same direction it's moving, you just multiply your force and distance, which makes sense because work is the force in the direction and the displacement it moved if they're the same direction. But what if it's angled? So most of the time you're going to get a problem where the force is not directly aligned in your displacement. So like for example, we have this block and maybe someone's pulling it with a string at an angle with the ground. So but the block moves forward. What is the work? So we have to use vectors as we used in kinematics. We can do the same thing with forces. We can break them up into vectors. So we have, remember our trig functions, cosine, sine, and tangent. Those are very helpful outside of just math. So we can use cosine and relate it with the hypotenuse and adjacent side. So and then sine we can use for the opposite side. So this is very important. So if cosine is adjacent over hypotenuse, so if we use f cosine theta, we will solve for this component. And if you haven't reviewed that in trig class, just look at my video on kinematics, on two-dimensional kinematics, and I'll quickly review about how exactly to get this. But basically, the force in the x direction will equal f cosine theta when theta is measured with the ground. So when it's measured with the ground, f cosine theta will always give you this x component force. And then you just multiply f cosine theta with the distance, and basically you get our formula: work equals fd cosine theta. And so it's the same principle. You always multiply the force in the direction of the movement with the distance it moved. So in this case it'll be f cosine theta because it's only a part of this force, and then you just multiply by distance. So work is always fd cosine theta. Okay, so here we have a typical problem where we have to calculate work. So a person is pulling a block 45 degrees from the displacement at 50 newtons. The block moves 5 meters. So before solving these problems, it's pretty helpful to draw a picture of the scenario. So here we have a picture. This is what I imagine. So we have a block here. We have this dotted line represents displacement of 4 meters. the person was pulling with 50 newtons of force at 45 degrees from which the block moved. So if you imagine this picture, uh, good for you. So always when you're starting out with these problems, just draw a picture and it'll clear things up really well. So basically, if we look at our formula, work equals FD cosine theta. We have the force, 50 newtons, right here. We have the distance, which was 44 meters, sorry. And we have theta between force and distance, which is 45 degrees. So basically, we just plug that in our equation and we get our answers. And it's important to know work is always measured in joules. And to give you an idea of what joules means, a joule is measured in kilogram meters per second squared or Newton meters. So, and it is the equivalent of moving a 100-gram object 1 meter. So just think about the force it takes to move a very small apple 1 meter. So a joule is just basically a small, very small amount of energy. So 1 joule is moving 100 grams 1 meter. So 2 joules would be like moving 200 grams 1 meter. So you get the picture. It's just a very small amount of energy. That's the important thing you need to know. So what about this scenario? So we talked about how work is the force in the direction of the displacement times the displacement. So in this case, since force is not at all in the direction of displacement, it's perpendicular to the displacement, the force does no work in this scenario, this force. Even though we have a arrow showing the force the guy's holding up his suitcase with, it does no work because work is the force in the direction of the displacement times the distance it moved the object. So since the force is not at all, there's no component of this force that pushes to the right here. It's all straightforward, I mean upwards. So nothing, not even a single piece of the force pushes the way the man's walking. So this force does no work. His arm does no work in physics. According to physics, his arm does no work while he's moving. So even if you don't get that and you're more of a mathematical person, we can prove it mathematically also. So because work is FD cosine theta, the angle between the force, which is straight up, and distance, which is straight to the right, is 90 degrees, and cosine of 90 is 0. So therefore, if we plug in 0 into this formula, there is no work being done by that force. So there must be another force. Whenever, I mean, in this case, there must be another force moving the suitcase towards the direction he's walking, because his arm is doing nothing according to physics, because his arm is pulling it upwards, but the suitcase is moving to the right. So does that make sense? How can a force is totally perpendicular to the direction it's moving affect the movement? So basically, if a force is perpendicular to how it's moving, that force does no work to that object. So now we're going to talk about energy. And so there are two types of energy I'm sure you have all heard of: kinetic and gravitational potential, or potential energy. And so kinetic energy is the energy in the form of movement. So anything moving has kinetic energy because kinetic means moving. Like kinematics is a study of movement, kinetic is movement or moving. So kinetic energy is 1/2 mv squared. So 1/2 mass times velocity squared. And gravitational potential energy is the energy caused by an object's position over Earth or over in another, like a planet or a bigger object. So if work is force times distance, when lifting something against gravity, the force is mg. And so this has to do with, because the object's mass, the greater the mass is, the greater the gravity is, or the force of it to lift it. So if you think about it, if you're like lifting like a dumbbell or something, the heavier it is, the more force it takes to lift it. So whenever you're lifting something, the force is the mass of the object times the gravity. So, and then the displacement in this case is the height, because let's just say you're pulling it straight forward, the distance, because work is force times distance, the distance is the height. So therefore, the gravitational potential energy, or U sub g, equals mgh. And that is the formula for potential and kinetic energy. So, and this is gravitational potential energy. And for some reason, they use U to symbolize potential energy. And so, basically, this shows how energy can be converted. So we have kinetic energy at the bottom. So this bicyclist is moving to the right. He has a lot of kinetic energy. Then he goes up the hill, gets potential energy in the form of gravity, gravitational potential energy. And then as he goes down, some energy from potential energy is converted back into kinetic energy. So this shows how kinetic energy to potential to kinetic. And the third energy we usually deal with is potential energy in a spring. And so U sub S, so potential energy sub S is spring, is 1/2 kx squared. And so here I'm going to show you the derivation of why is there a x squared in a squared term in this formula. And so if we look at a graph of force and distance when a spring is stretched, we will get a graph just like this. So force is on the y-axis, distance is on the x, and we have a straight line. So remember back when we were analyzing kinematics graphs, we knew two important things you can read from a graph: area and slope. So the slope of this graph, so basically, if you think about a line, force, which is the y term, so y equals kx. So in this case, force equals the slope times the distance, which I represented by x. So this law is known as Hooke's law. So force of a spring is the spring constant, which is the slope, and times the distance that the spring is stretched. So Hooke's law says that for every meter or distance you pull the spring, the force is proportional to how far you pull it. The area of the graph is work, because if we multiply the units, force times distance, we get work, because work equals force times distance. And the units of slope, by the way, are Newton meter, because force is measured in newtons, distance is measured in meters, so newtons over meters equals the units of the spring constant, K. So that is also important. So always, when you're analyzing slope and area, always analyze what it is and the units of it. So the slope of this happens to be the spring constant, which is something new. It's called Hooke's law. And then the area is work. So that is a cool way of how we relate a graph with work. And so because work is, in this case, the area of the graph is 1/2 base times height, because we have a triangle. 1/2, and then base is the distance, height is the force. So we basically have 1/2 force times distance. Okay, and since Hooke's law says that force equals slope, or K, which is the spring constant, times distance, or x we're going to call it, we plug this in, so 1/2 fx, which we got from here, or yeah, fx, times x, and we get 1/2 kx squared, because force is kx, and distance is just x. So if we plug that in into what work equals, we'll get 1/2 kx squared. And sorry, by the way, I forgot to put, this should be a k, not an f. So 1/2 kx times x equals 1/2 kx squared. So basically, the slope of this line is the spring constant, k. And so force equals kx. And then the area of the graph is work, which is force times distance, which is work. So the area of this graph is 1/2 base times height. Base is distance, height is force. And we know from Hooke's constant, that's the whole point of the slope, force equals kx. So if we plug that into our work equation here, we will get this formula. So that is a little bit about how to derive the potential energy of a spring. And so all three of these energies, kinetic, gravitational potential, and potential energy of a spring, all are referred to as mechanical energy. So if you ever see mechanical energy, it's referring to those three types of energies. And the important part about energy is that it is always conserved, because energy cannot be created nor destroyed, but it can change forms. And so basically, ultimately in real life, when energy is transferred, some of it will be lost as heat, but technically it's not destroyed, because it's just not usable, because in real everyday life there's always friction. And so most people think that whenever there's friction, energy's destroyed, but not really. It's just being transformed into heat, which is just not usable in our case. And most of the time when we're solving for, like, in energy problems, we will solve for like height, or velocity, using kinetic, potential, energy of gravity, and spring. So that's how this is the type of problems we will do when converting from different forms and stuff like that. And so here's another important piece of information we should know: the work energy theorem. So basically, we will relate work, energy, and acceleration. So we know that work is force times distance, and force equals mass times acceleration. which is Newton's second law, and we will talk more about this, but in this case, all you have to do is know these two formulas. And since force equals mass times acceleration, we can substitute it into the work formula, and we get work equals m mass, acceleration, and d, or distance. So work equals mad. And then if we use the energy formula, if you remember back from kinematics, uh, final velocity squared equals initial velocity squared plus 2ax, and solve for acceleration. So basically, you move everything to the other side except a. We will get acceleration equals final velocity squared minus initial velocity squared over 2x, or 2 times the distance. And if we plug this in back into work equals mad, we'll get work equals mass times this thing here. And if we simplify this, so basically if we distribute the m and x, or I mean cancel out the x's and distribute the m to the two terms here on the top and the 1/2, we basically had that work is the change in kinetic energy. So basically, if we have an object moving and it slows down, the work we did, or something did to that object moving, is the change in kinetic energy. So see, 1/2 mv sub f squared, so this is the final velocity squared, 1/2 mi squared, so initial velocity squared. So basically, this is kinetic energy at the end and kinetic energy initially. So basically, work is the change in kinetic energy, and that's what the work energy theorem represents. And this is how we can prove it through Newton's second law, the energy formula, and work. And this is an important piece of information. Why is that equation we just used, the energy formula, really called the energy formula? We derived it with kinematics, but the important part is it can also be derived through energy. And so this is pretty cool how you can derive this one formula two separate ways. And here, let's take, for example, this scenario. You have a ball that's at the top and has initial velocity, and it falls down and has a final velocity. So conservation of energy, assuming there's no friction, says that initial energy equals the final energy. At the beginning, we have kinetic and gravitational potential, 1/2 mv squared, mv sub I squared, because initial velocity squared, and then mghi, so initial height. So mgh, yep. At the end, we have kinetic energy and gravitational potential energy. So instead, 1/2 mv sub f squared, so final velocity squared, and mgh, so the final height, h sub f. If we combine these and set them equal to each other, because conservation of energy, initial energy equals final energy, we know or if we subtract each side by mgh sub f, so if we subtract each side, this from each side, and now since all of them have a m, or a mass, we can cancel that out. So if we cross out all the masses and cancel this out, we will get 1/2 v sub I squared plus g delta h equals 1/2 v sub f squared. So if we multiply 2 into every term, basically these 1/2 cancel out and this one gets a 2, we will get this equation. And this looks very similar to the energy formula. And the only difference is really we have a g and it's negative. And that has to do with gravity being a negative acceleration because it's always downward. So that is the only difference between the energy formula and this formula. So this is how you can derive the energy formula using energy. And this is a cool way to that you know how to derive this formula using 2 separate ways. So that shows how the 2 principles of kinematics and energy actually work together because they both derive this formula. So thank you for listening to my physics video today. Today we learned about work, types of energies, and some derivations. Tune into the next video to learn how to solve basic energy problems and actually apply what we learned today. And if you had some confusion with the derivations, just revisit them, write them down on your own piece of paper. Like, you try to, watch the video, play it a few times, and then, pause the video and close it, look away from the screen and try to do it yourself. So that is truly how you can learn how to do derivations and really understand them. And please, if you enjoyed this video, please spread the word and tell your friends that are also taking physics or just interested, and please like the video down below. If you have any questions and comments, please email me at mpatelbuccaneer@gmail.com. And I know some of this stuff can really be confusing at first, but if you keep on, practicing, I am sure you will understand this. And it's always important to ask questions, so please email me any questions, especially about work and how things have to be perpendicular, anything with angles like vectors, or just knowing how to derive the spring constant formula. I know that sometimes can be really confusing, how you can analyze a graph and then the area and put it all together. And so for any if you're taking chemistry, please visit my chemistry tutorials at my website, buccaneerchemistry.weebly.com. And so tune in next time and we will learn how to solve some real energy problems. And I hope you have a great day, and we'll see you later.